So indeed, this will be about optimization on manifolds. So the goal in this talk is to optimize a smooth function on a smooth manifold. So just a picture that summarizes this problem is here in the case of this picture, the manifold would be a sphere, simplest one to draw. And on that surface, on this smooth surface, there's a cost function that's defined. And what we see here are the level sets of that function. And we're trying to find, ideally, the global optimizer of that cost. So ideally, we would like to compute this point over here, okay, by using some numerical method. And the method that I want to use and to modify a little bit in this talk is the so-called Riemannian truss region method. And so before I get into that, I'd like to go back to the basics of what the truss region method in the classical case is. So actually, maybe a show of hands. Who knows about the truss region method? Yes? Okay, so not everyone, which is good because I wanted to explain this going back a little bit. And very often people know about the Newton method. So if you forget about manifolds for a second, so you have a smooth function that you're trying, and there's no constraints, you're trying to minimize it. Then the Newton method, what it does is it says, give me a point, and maybe your function is a bit too difficult to handle, so I will locally approximate it by a quadratic, by a second-order Taylor expansion of that function locally. And if that quadratic approximation is convex, is like this, then I can go to the minimizer of it, which is easy to do, because it's just a quadratic. So give me a new point, and then I can iterate this. And if some conditions are met, then we know that the Newton method will converge to a local optimizer, hopefully, of my function. Now, I'm saying if some conditions are met, because of course, it might happen that at the point where you're looking, the quadratic approximation is not like this, but it might be something like this, in which case going to the critical point of the quadratic is not going to do you any good. And so this has led people to modify the Newton method a little bit into what is now called the truss region method, where you say, we're going to keep the basic idea of Newton, is we're going to keep the idea of locally approximating with something quadratic, but we're not going to globally minimize as quadratic, because sometimes it will do something weird. Instead, we're only going to minimize this quadratic model in a truss region, like in a small ball around my current point. The idea being, it's a local model, so I should only trust it locally, okay? And this has been around for a while in unconstrained nonlinear programming, and it has been maybe almost 10 years ago, it has been adapted to also work if you're trying to do optimization on manifolds. And so we know how to do this as well, okay? And so what this might look like on a manifold is like this. So we have, again, our problem. Our search space is the sphere. There's this cost function defined on the sphere, and I have a certain point that is given to me, okay, over here. And I would like to compute a better point starting from that one using this truss region idea. And what does it look like? Well, since I'm only going to consider my cost function close to my point, I might as well go to the tangent space, which is locally a good approximation of my manifold. And then somehow, and I'm going to describe this in a second, I can somehow lift my cost function to the tangent space, which will give me another function, but this time on a vector space. Because I'm in a vector space now, I can use the classical truss region idea of approximating this with some kind of a quadratic model, which will give me this problem. So now I'm in the tangent space here. The whole screen is a tangent space. What I see are the level sets of the lifted cost function. And xk over here is my current point, which would correspond to 0 in the tangent space. And inside trussed region, so within some distance, I'm going to optimize the lifted approximated cost function, which will give me a vector. And this vector corresponds to a tangent vector to the manifold. And then how do I get my next points with this algorithm? I just follow this direction. So I move away from my current point, following the direction that I just computed in the tangent space. And this brings me to a new point on the manifold, and I can just iterate this. And then under some conditions, this will converge indeed to a critical point. So this will converge to a point where the gradient of my cost function is 0, and in practice, we actually expect this to converge to at least a local optimizer. Okay, so this is the basic framework. And there's a number of things that I skipped in this explanation. One is, how do you do this lifting? How do you bring back the cost function to the tangent space? So that I'm going to explain right now. And the other thing that I did not explain is, how do you approximate your cost function? Like I said, you can use a quadratic model, but what do I mean exactly? And this is going to actually be the topic more specifically. Okay? So again, you want to do truss regions on a manifold. The first thing is you lift the cost function to the tangent space. Now you're in a vector space, so you can just open any book about truss regions and do what they say to do. And then the answer of this step is a tangent vector, which you then have to map back to the manifold. But so there's this, how do you lift the cost function? And once you did that, then you have a tangent vector. How do you map back to the manifold? Then, of course, one way would be to use simply a geodesic, so the exponential map, which is a word that you can use in this conference without having to explain, so that's nice. But you could also use something that's more like an approximation of a geodesic, because very often geodesics are quite expensive to compute. For example, something we use on the sphere is simply this idea. If you give me a point x and I want to move along the vector x dot, so this would be x dot here, you can simply do the addition in the embedding space. Of course, x plus x dot is not on a manifold anymore, but you can simply project back to the manifold, and that's a valid approximate geodesic that we're going to call a retraction. Okay, and if you use retractions, then you can use them to do this lifting. Okay, so how do you do that? So you have this cost function f is defined on a manifold, and you want to move it to the tangent space, and what you can do is simply take the composition of your cost function with the retraction. Okay, so the retraction maps from the tangent space to the manifold, and the function f maps from the manifold to the reals. So when you compose them, you indeed get a function that goes from the tangent space to the reals, and this is going to be our local model, or lifted cost. Okay. And now that we have this notion of a lifted cost, I want to be a bit more precise about what I mean by approximating. So we have this function on the tangent space, and now I want to define a new function, which is going to be called m. M is the model, and m is supposed to approximate f hat. Okay, and the canonical way to do this is to start with at least a first order Taylor expansion of the lifted cost, which happens to coincide with the first order Taylor expansion of the true cost, because the retraction doesn't distort things to first order. So this is a valid first order approximation of both f hat and f. I'm going to add that my model be at least this, so that we agree to some extent. And then I'm allowed to add some extra term here. Okay? And if you think of hk as being a linear operator, and this is exactly what we're going to change later, we're going to make hk nonlinear. But in classical theory, we will only consider hk to be a linear operator. And what the theory tells you is that you can pick any linear operator for hk here, and the truss region method will still manage to somehow converge to a critical point. Only you expect, and indeed the theory tells you, that if you take hk to actually be the Hessian of the cost function, so that this model would be even more accurate than just first order, then you would expect that this method would work better. Okay? And this is indeed what we see in experiments. So here, I just picked some random optimization problem on a manifold, ran truss regions on it, and in one case I used the true Hessian, which is the blue curve here, and in the other case I just approximated the Hessian with the identity. Okay? So a very poor approximation. And what we see here is the gradient norm on the log scale. So we see that in both cases, the truss region method converges to a critical point. Okay, it's like gradient is almost zero as time goes by. Only, of course, with the true Hessian, you do so much faster. Here you see something that's characteristic of a superlinear convergence rate, whereas here it's quite typically a linear convergence rate. Okay. So then the conclusion, based on just this one experiment, is okay, sure. So now I'm going to compute Hessians, except computing a Hessian is a pain, and I've never computed a Hessian just to see what happens. Like before I compute a Hessian, I always want to be sure that it's going to be useful. And so it's tempting to try and modify the truss region method so that it would work with some kind of an automatically defined approximate Hessian that you don't have to work too much for. And so one thing that I think is tempting is to use finite differences. And so I don't know if this goes up, or can you all see the board if I write here? Would that be fine? Okay, thanks. Okay, so forgetting about manifolds once more, if we just have a cost function f defined in Rn, and I want to approximate the Hessian of f at some point x along a given direction x dot. So this is a linear operator that I want to apply to the vector x dot. I want to approximate this, but using only knowledge about the gradient, because computing gradients is reasonably easy. So I'm going to ask the user to compute gradients, just not Hessians. So it's a very well-known fact that we see early in college that you can approximate this with something like this, right? So we're going to compute the gradients not at x, but somewhere further along the direction x dot. Compute the gradient there, compare it to the gradient at x, and divide by the step size. And this should be, a good approximation if t is sufficiently small. And then you have to make t not too small, because otherwise numerically things go wrong. But at least you expect that this should be not too bad. And when you want to do this on a manifold, then you have to adjust things a little bit, because while x plus tx dot is not a well-defined operation, we're not on a vector space, but you can use the retraction, right? This thing here is just starting at x, move a little bit in the direction x dot, and that's exactly what the retraction does. So that's the blue part over here. And then the other thing is that these two things here, they're both vectors, but they're vectors in different tangent spaces. Okay, one is in the tangent space at x, the other is in tangent space at the retraction of x at tx dot. So you have to, this is the green part, you have to somehow transport one of the vectors to the other tangent space so that you can compare them. But if you're willing to do that, then you can use this kind of expression to approximate the Hessian using only knowledge about the gradient. And before doing any theory, you can just code this, put it in the algorithm, and see what happens. And this is typically what you see. You have this yellow curve here, behaves almost exactly the same as if you had the true Hessian, just in this case it's a bit slower. Sometimes it's even faster, actually. It depends on the application. And you seem to get all the benefits of the Hessian, even though you didn't have to compute it. But the issue is, there's no theory. Like the theory, the classical theory breaks down when you use this approximation of the Hessian, because this operator here is not linear. Okay? And this has nothing to do with the fact that we're on a manifold. Even here, this is not linear because you compute the gradient as an input that depends on x dot, but of course the gradient is not linear in its inputs, right? And so this operator is nonlinear, which means that the classical theory doesn't apply, and then you have nothing to, you have no guarantees at all. Okay. So the simple idea of the paper that we propose here is simply to look inside the proofs of convergence of truss regions and see if we can modify it just a little bit to make it work with this approximation. And it turns out that yes. And this is actually something I'm quite fascinated with, is the classical analysis of truss regions is remarkably robust. It asks for very little things, very few key things that you need to have. And if you have those, then there is a very clever machinery of analysis around it that just makes it work. And the two things you need are quite natural in a way. Looking at the first line, you need the model to agree with the cost at least somewhat. Okay, and the reason for it is that at each step we're minimizing the model, not the cost. But in the end, we want to minimize the cost. So of course there has to be some kind of link between the model and the cost, otherwise nothing gets done. And looking at the third line, the other thing is that at each step you need to be sure that you will decrease the model at least a little bit. Okay, because if you are unable to minimize even the model, even though the model looks like the cost, nothing would happen either. Okay, so but if you have both of those things, then there's clever machinery that shows that the truss region method will converge more or less independently of what other things you do inside of it. And more specifically, for the first requirement, we need f hat and m hat to agree to agree in this fashion that the error term should be quadratic. So if you remember, m hat at x dot, that was f evaluated at xk plus the inner product between the gradient of f at xk inner product with x dot plus 1/2 and a quadratic term. A quadratic term, x dot hk applied to x dot. Something like this. And so, okay, and then f hat k at x dot was the composition of f with a retraction. So it's f composed with a retraction at xk of x dot. But we know that this here is the first order Taylor expansion of this. This is something that I imposed. So when I look at the difference between f hat and m hat, the difference between this and this will already be of second order, will already be proportional to x dot squared. And so in order to satisfy that condition, I just need to make sure that this is also bounded by some constant times x dot squared. And of course, if hk is linear and uniformly bounded, then that will be true. But I don't need hk to be linear for this to be true. I just need it to be radially linear. Okay, I just need that hk, if I apply hk to some vector, or if I apply it to 5 times that same vector, I need linearity along such rays. Okay, I need this to be 5 times what I had before. But I don't need hk along x1 plus x2 to be hk along x1 plus hk along x2. I don't need this to ensure this kind of error bound. Okay, and this is good news because I can simply modify the finite difference approximation a little bit to make sure that it is indeed radially linear and not completely linear. Just by, we had a t here. This was the step size t here. That I'm scaling it in proportion to the norm of x dot, so that if I apply this operator to x dot or to 5 times x dot, I will get this kind of linearity. Okay? Because if x dot is 5 times bigger, I'm going to divide by 5 times bigger, which means that I'm going to look at the same point, and I'm going to make up for that by multiplying by 5 over here, which means that along every single ray, I will have linearity, just not along composition of rays. Okay, and this means that with this formula, I have radial linearity. And then if I also show that these are uniformly bounded, which is going to be some kind of a Lipschitz assumption on the gradient, then I'll be fine. Okay? And the second thing that we had is that at each step, I need sufficient decrease in the model. Now, if hk were linear, then we would have some kind of quadratic that's possibly non-convex, but that's fine, to minimize inside the ball. And it so happens that this is polynomially solvable. But now it's not a quadratic anymore, right? Because we have this nonlinear term. But that's fine, because to get a sufficient decrease, you actually don't need to solve the subproblem completely. You only need to solve it at least as well as if you were only allowed to look along the steepest descent direction. I'm going to say that again. So the subproblem might be a problem in pretty high dimension, right? You have this ball in as many dimensions as the dimension of the manifold. You're in the tangent space. And you have to optimize this possibly complicated model on that ball. That might not be easy. But what the theory tells you is that if you just look along one direction, which is given by minus the gradient, then you're sure that along that direction, it will be possible to decrease the model. Okay? Why is that? Because if x dot is minus the gradient, then you'll get some linear improvement over here in the size of x dot, and this will be quadratic. And so you will be sure to, at least if you make a small step, you will get a decrease. And actually, that decrease that you get along that specific direction, if you at least get that at every iteration, that's enough to get global convergence. Okay, and so then the strategy is quite simple, is just look along that direction. Because along any given direction we are linear, this is going to be just a parabola to minimize in an interval. Okay, so extremely simple, you just do that. Then do whatever else you want that seems smarter. And if that fails, just pick the thing that you had before, okay? And there's an easy way to put this in music. And so this is what we do. And I think I went over this more or less. So we show that the finite difference operators are indeed bounded, which you need to control the errors. We show that if you take what people usually use to minimize the inner problem, and you just modify it to be sure that you do at least as well as this minimization along minus the gradient, then you get the sufficient decrease, even though it's nonlinear. And with both of these things, you can show that you get global convergence to critical points. Okay. Now the caveat is that it's a quite mild guarantee, because we say nothing about how fast you get to the critical point. Okay. And the reason for this is that the proofs that control the rate at which you converge to the critical points, they have to do with what happens in here. And this is a conjugate gradient method, in fact, that takes place on the tangent space. And the conjugate gradient method relies very deeply on linearity of HK. And making HK nonlinear appears to be a deal breaker. All right. So that's it for the talk. I just want to mention that all the algorithms that I talked about, they're available in Manopt, which is a MATLAB toolbox that you can use to experiment with optimization on manifolds. And in fact, this finite difference approximation of the Hessian is something that's been in the toolbox for years, and that just works. And so we wanted to, at least say something about it. But thank you.
Maybe one or two quick questions. I will use the microphone.
Sorry, thanks for the interesting talk. I think I missed a couple of minutes at the earliest minutes of the talk, but you assume that F is always convex or concave, or?
Neither of those, because F is defined on a manifold, which itself is typically non-convex, and so the notion is not particularly relevant, but we do assume that F is sufficiently smooth.
Okay, just one more question. Do we always assume that the manifold, the structure of the manifold is like that at every single point tangent space is a good approximation, or for example, we might, based on, for example, inverse function theorem or implicit function theorem, we might be able to show that a surface is manifold, but there is a tiny high curvature in the manifold that tangent space may not be a good approximation. How does this work, the algorithm work in those situations?
What do you mean not a good approximation? It would just be not as good, or there would be something fundamentally different happening?
No, not as good. For example, if it's a sphere, well, we know that tangent space is always a good approximation, yeah? Mm-hmm. But imagine like a sort of, in 3-dimension, like sort of ellipse, but with one direction really much bigger than the other one. So the tangent space at this peak is really not a good approximation for the manifold. I just want to know that how this second quadratic term helps, just the algorithm to be.
So there's two aspects to this. So the truss region mechanism will automatically adapt the size of the truss region to what seems to be happening. So what that means is you will minimize the model, which gives you an expected decrease in the actual cost. And then you compare that to what you actually got. And if there's a huge difference, then you will decrease the truss region radius, which means that the method will automatically scale down if it sees that it's in one of those bad regions. So that's one thing. The other thing is that the result I talked about is purely asymptotical. It says that asymptotically you'll get there to a critical point, but it says nothing about rates or constants or whatever, and I expect that what you're describing would have an effect on the constants in that kind of result. So the result I talked about says nothing about the situation you describe, because it just tells you what happens at infinity. But if you did a finer analysis, probably that would show up, I imagine, because it has to hurt you somehow.
Yeah. Thank you so much. I have another question I'll ask you at the end of the session.
I apologize. I think we should stick to schedule because people may also want to switch between the sessions. So I propose that we thank Nicola again.